this lecture, we'll see how we can form a category whose objects are categories themselves. So to begin with, let's understand the notion of composition of functors. So suppose we have categories C, D and E. And we have functors C to D, we have a functor F, and D to E we have a functor G. Then we can define a functor from C to E, and I'll call that G circle F. As follows. So remember, to define a functor, you need to define it at the level of objects and at the level of arrows. So at the level of objects, it's going to be G circle F of A is G of F of A. This makes perfect sense because F of A is an object in the category D, and then G is a functor from D to E, so this is an object in the category E. So G circle F of A is an object in the category E, and so this is for every object A of C. And on the level of morphisms, we can define it similarly. For every arrow F in the category C from A to B, we can define G circle F of F to be G of F of F. So notice here that F of F is from so F is from A to B, and then F of F is from FA to FB. This is how functors work. And then G circle F of F is from G of F of A to G of F of B. And this is an arrow in the category E. And so this defines the composition of functors. It's easy to verify that in fact G circle F is a functor. You need to check that it respects identity arrows and composition of arrows. If you want, you can try to do that. Okay, so so you can compose functors, and so this suggests forming a category of categories. So so we'll say that C is a small category if its collection of objects is a set and its collection of arrows is also a set. If you're not interested in set theory, you can ignore this definition entirely, but this is needed in order to prevent issues like Russell's paradox from cropping up. So now I'll define the category of categories. So cat, this is the category whose objects are categories, are small categories. And the arrows, so given categories C and D, the arrows from C to D is the collection of all functors from C to D. And as we've observed, there is an identity functor from each category to itself, and also we can compose functors. So you can check that this cat satisfies the axioms for being a category. And this thing about small categories, you needn't worry about it too much. For most practical purposes, we can um, replace our large category by an equivalent small category by making some technical restrictions. So we won't worry about these issues with small categories and Russell's paradox. I'll gloss over them completely in this course, but you can look at McLean's book for more details. Okay, so let's just play with this category a little bit to become familiar with it. So here's a question. What is an initial object in cat and what is a final terminal object in cat? Okay, you can pause the video now and take a minute to try to think what the answers are. Maybe the category of sets can give you some motivation. But here's the answer. So there's a category which I'll denote by 0, maybe underline 0. Denote the category with no objects and hence no arrows either because there are no objects. And this is an initial object in cat. Indeed, given any category C, there's only one functor from 0 to that category C. The functor doesn't have to do anything. You can think of it as the empty functor. It doesn't there are no objects in O, so you don't need to associate to any. So there's nothing to associate, and that's the only functor there is. And there's another category which I'll denote by 1. With one object, let's call it star, and it has only one arrow, namely the mandatory arrow, the identity of star. And this turns out to be a terminal object in cat. Given any category C, you can define an arrow to this category 1 by just taking every object in your category C to this object star of 1 and every arrow of your category C to the arrow identity star. Just check, think about it, and make sure that this makes sense to you. And we can also do other universal constructions in the category of categories. Let me give you an example. Let's talk about the product of two categories. So given categories C and D, we'll construct a category called C cross D. So let C cross D denote the category. So I need to specify what are the objects, what are the arrows, and what is composition. With objects of the form C comma D, where C is an object of C, and and D is an object of D. And what are the arrows? So in the category C cross D, let's take two objects. So let's say C1 comma D1, and let's take another object C2 comma D2. So here C1 and C2 are objects in the category C, and D1 and D2 are objects in the category D. Let's write this neatly. And this is defined to be just pairs of arrows, the collection of all pairs F comma G, where F is an arrow in C from C1 to C2 and G is an arrow in D from D1 to D2. And then given objects, given arrows, so we suppose we have C1 D1 to C2 D2 and then to C3 D3, and here we have say F1 G1 and F2 G2. So given such arrows in C cross D, the composition is defined by F2 G2 circle F1 G1 is component wise composition F2 circle F1 G2 circle G1. So this defines the category C cross D, and I claim that this category is a product in the category of categories. So this C cross D comes with two functors. C cross D has a functor to the category C and a functor to the category D. I'll call these functors P subscript C and P subscript D. And these are the projection functors. P subscript C of C comma D is going to be C. P subscript C of F comma G is going to be F. P subscript D of C comma D is going to be D. P subscript D of F comma G is going to be G. So this defines, you should check that this defines functors from C cross D to C and D. And moreover, this category is going to satisfy the universal property for products in the category of all categories. So given any category E and functors, so let's just take from E, suppose we have two functors, let's say FC and FD to C and D. Then we also have this C cross D over here, and we have functors PD and PC. We can construct a functor here F. And how do we construct F? Define F of any object E to be FC of E, comma FD of E, and given any morphism, let's say we have two objects E1 and E2 of E, we can define F of F to be Fe of F comma, sorry, fc of f comma fd of f. So that will give us a functor from the category E to the category C cross D. And this is forced for this diagram to commute, and you can check, so therefore, that this category C cross D satisfies the universal property for products in the category of all categories.